Welcome back, Physics 30. Today's lesson is half-life. And if you finish Math 20-1, you probably already faced some question like this because half-life, I believe you learn it in a series and sequence. But in any case, half-life, like the word suggests, if I have, let's say, 100% radioactive matter, how long does it take to have that original 100% into 50%? It's about that time. So half-life referring that time duration from 100% to 50%. Some of those chemicals, atom if you will, takes about some minutes and hours. Some of them take years. For example, when it comes to carbon dating for dinosaur, that takes millions of years to make 100% to 50%, something like that. So have that in your mind. And radioactivity is basically talk about the rate of radioactive emission, and that's a decay procedure by emitting alpha particle, beta, negative or positive, or gamma particle, something like that. Gamma radiation, sorry. And it is measured by Geiger count. And Geiger count use a unit known as Becquerel, BQ. Becquerel is, think about it like when you first learn about the current of an electricity. Current unit is amp, which is technically Q over T, which is how much coulomb of charge per second in a certain area, something like that. BQ, Becquerel, basically means the same thing. It's one emission of a particle per second. So it is a unit of rate. And the person that mentioned in this section, which you probably heard before, Madame Curie, one of the very first Nobel Physics Prize winner, Curie. Madame Curie basically discovered that radioactive is not affected by things that affect chemical reactions, such as like external factor, like temperature, pressure, or bonding with other atoms, like hydrogen bonding, intermolecular to intramolecular, which is within like Lewis-Stahl diagram in chemistry 20, you may know, like covalent bond. But in any case, there are only two factors that affect radioactivity. One is their mass, so how much it is available. Sometimes it doesn't start with 100%, depends on the question, but in any case, initial amount. And number two, the half-life of the radioisotope. So without further ado, let's go with this graph, an example. Half-life, like I mentioned, it is the time required for half of the atom in a sample to decay, or 100 to 50, or 50 to 0. You can think it in that way. It can be 80 to 30 even. But all the isotopes have unique half-life. For example, thorium-234, when it comes to day 0, of course, everything, 100%, is parent nucleus. It's like your initial momentum, if you will. You didn't have any of a conversion of that momentum into something yet happen. Or initial energy, potential to kinetic, something like that. Or vice versa. Day 24, now this 100% thorium-234 is now getting less because some of the particle will be emitted during that time. And 50% was other atom. That can be basically daughter nucleus plus some kind of other particles. It can be alpha, beta, whatever that can be. And if you let the clock pass more, then naturally you will have only this proportion, 25% in this case, you will see. And that graph pattern, you can find it from the right side. If you take Science 30, this science 20 more, I guess. This graph is given, you need to match which one is which, something like that. But half-life, like the word suggests, 50% is where you need to focus. So if you have any graph given, you just need to trace that. And the time that make 50% from the 100% happen, this is known as half-life. And it's exponentially decreasing. It looks like inverse relationship, if you will, but talking about inverse relationship, this is a formula. The one on the left is given, one on the right not given in your data booklet. So when you see big case N, think about that as NF, final amount. And that can be gram or percentage, something like that. When it comes to N0, that's original amount, so initial amount. And half time, mathematically, 1 over 2 and to the power of n, this n is basically what I like to call it as number of half-life. So how much 50 of 50 of 50, those kind of thing happen. To understand that, you need to use this formula though. Total time over T1 over 2, which is half-life. This formula is not given, and know the fact that when it comes to time, if it's second, minute, hour, unit cancel, so n is technically unitless. Have that in your mind. So, without further ado, let's do some example. Now, there are two types of example. One is easy type, one is a little bit tough type. Easy type is literally punching the number in and answers find out as a result. The tough type is basically you need to go through inverse log or natural log. That's how you can reverse some of the exponent. But in any case, a total time of 116 seconds is required for a radioisotope's activity to decrease from 1500 becquerel to 93.75 becquerel. So, first thing first, total time is given as 116 seconds. And from 1500, that's my original, and it's okay, it doesn't have to be exact amount, it can be rate 2 like what I said, 1500 becquerel, and my final was turned out to be 93.75 becquerel. The question is asking you to find out how much is your half-life. So this is a going backward type of question. It's a little tricky type of question, and I'm going to explain to you why. But anyway, first step, list everything. Second step, you need to go to the formula. Now, the formula, we have n arrow, so that means we need to use the formula that is given by the question, or data booklet if you will. I have n is equal to n0, 1 over 2 to the power of n. We are basically trying to find this guy, because n is equal to total time over half-life. In order to do that, isolate these guys first. So n divided by n0 is equal to 1 over 2 n. Now, here's your dilemma. You're trying to find n is equal to, but right now I have exponent and the base in here. How can I reverse this order? You can do logarithm or natural log, which you can find from your calculator. Logarithm or ln, natural log. It doesn't matter which one you use. So I'm going to use natural log because that's one of my, go-to. It's easy. But if you like to go logarithm because you did math 30-1, then please feel free. So the way that you do is this. One of them, you need to put it on left side and right side. So if you use natural log, it will look like this. If you use logarithm, it will turn out like that. It doesn't matter which one you use, but in any case, let's solve this question and isolate for n. So n is equal to natural log n divided by n0 over natural log 1 divided by 2. And now I can punch those numbers in. 93.75 divided by 1500 divided by 1 divided by 2. And n values coming out as a result. Oops. And you have 4.00 or exact number 4. But that's not my final answer. That is basically my total time over t1 over 2. So which is 162nd over t1 over 2. So if I rearrange the formula, 116 divided by 4, and that's turned out to be 29 seconds. This is one of the tough example of a question. Now, let's do one more, but this time I like to do there's not much of an easy question. There is the one that is involved with the graph on the next page, so let's go with that. Generally easy type of question, the one that involves a simple punch the number in, can be found as a graph. What I'm going to go through is basically how can I say, I believe I can do D. Using this graph, we need to answer iodine 131 isotopes decay and half-life question in here. The mass of 24 gram of iodine 131 after 4.0 days, we need to find that. Now, here's the thing. First thing first, mass is located as 24 gram of it, but 4.0 day is located over here. That means you need to track everything 444 all the way up, then you reach eventually 70% of the mass or 70% of a sample. So what you need to do is basically simple ratio. 70% converted into decimal or fraction, doesn't really matter. Then 24 multiplied by 0.70 give me easily about 16.8 gram, which is around 17 gram. That's an easy type of question. Without further ado, that is my lesson for today. I want you to give it a shot for every question on page 13 and every question on page 14.